The goal for today's lesson is to be able to graph and solve systems of linear inequalities. Systems of equations are two or more equations on the same graph. So systems of linear inequalities are going to be two or more inequalities on one graph. Now remember, with inequalities, this is the one where we're going to either do a solid or a dashed line, and it's either going to be shaded above or below those lines to create some shaded regions on a graph. So since we're going to be graphing, let's remember when we're graphing y equals mx plus b that the m is the slope, also known as the rise over the run, and the b value, so whatever it's added to, is your y-intercept. So that's going to be where the graph starts or crosses the y-axis. Remember also that when solving an inequality, you must flip the inequality sign when multiplying or dividing by a negative number. Anytime you multiply or divide, just like we did with absolute value equations, if you multiply or divide by a negative, you have to flip the inequality sign. As a review from concepts from Algebra 1, remember that the two symbols, less than and greater than, the first two you see in this table, those generate a dashed line on a graph. So if you're using that symbol in an inequality, there should be a dashed line on your graph. And if you have the or equal to symbols, which is less than or equal to, greater than or equal to, the line will be solid. So that creates the difference in the two dashed versus solid lines. The dashed line falls through it, so those are not solutions. And since it's solid lines, the or equal tos create solutions. You also have some shading. So whenever you have either of the two less than symbols, you're going to shade in below that line, either the dashed or solid line. But if you have either of the two greater than symbols, you're going to shade in above. So less than is below, greater than is above. But what does it mean for something to be a solution to a system of linear inequalities? It's a great question. A solution is an ordered pair that makes all of the inequalities true. So we're looking for where the shaded regions overlap. We're looking for the super shaded region. In this first example here, and I would highly recommend having a couple colors to color with in this particular lesson, we have a solid line that is shaded above, and we have a dashed line that is shaded below, because it's below the dashed line, which creates then a super shaded region that is already graphed for you where those two regions overlap. This right here is called the solution set. The area where the colors overlap is called the solution set. So we can find or determine if an ordered pair is a solution just by simply seeing if that ordered pair appears in the super shaded region. So the coordinate pair 4, 1, remember this is x and y, is at 1, 2, 3, 4, and 1. Is that point in the super shaded region? Yes, obviously it is. Fabulous. Okay, what about the second x and y coordinate? That's at 0, 1, 2, 3, 4, 5. Is that green dot in the super shaded region? While it may be a solution to one of the inequalities, because it is not in the double shaded region, it is not a solution to the system of inequalities. While it's nice to have a graph to determine if something is an ordered pair, we are sometimes not given a graph. Sometimes we're just given a couple inequalities. Well, this is not a big deal because remember, we are given x and y coordinates, which means we can plug these x and y coordinates into each of the three equations and see what comes out of them. So for this first inequality, I will do this one in green just so you can see it. This green inequality says y less than or equal to 2x plus 3. But instead of y, what number am I going to plug in there? 0. And instead of x, what number am I going to plug in there? Also 0, because I'm checking the coordinate 0, 0. Then I just do some math. This sentence is going to say 0 less than or equal to 2 times 0 plus 3, or 0 less than or equal to 3. Is that a true or a false statement? That's a true statement. 0 is less than or equal to 3. So we try the next inequality. I'll do this one in purple. We're taking the inequality y greater than 4x minus 2, but we're plugging in a 0 for y and a 0 for x, making sure that I put those numbers in parentheses if necessary for substituting it in. Well, then my math sentence says 0 greater than 0 minus 2, or that 0 is greater than negative 2. Is 0 greater than negative 2? Yeah, so we have another true statement. We have to check the third one. Now, the third one I'm going to do in orange. Here's my orange equation. It says y less than x minus 2, but again, we are substituting in not y and x this time, but the numbers 0 for y and 0 for x. Well, this mathematical statement says 0 is less than, 0 minus 2 is negative 2. Is 0 less than negative 2? No, that's not right. So if any of your statements end up being false, like this one, you would end up saying, no, this is not a solution, because it doesn't work for all of the inequalities. It only worked for 2 of the 3. We need it to work for all of the inequalities. I'm going to have you pause the video here. I want you to take the x and the y coordinate that we are checking in these 3 systems, and I want you to check that coordinate in the green, in the purple, and in the orange equation, and just see if you get a yes or a true statement for all 3, so that that coordinate can be a solution. So plug in x and y. When you plug in x and y, we would be checking if y is less than negative 2 times negative 1 plus 3, which is like checking 1 less than 2 plus 3, or 1 less than 5, and that's a true statement. 1 is definitely less than 5. So we check the next one. This one is saying that 1 is greater than or equal to negative 1 plus 2, plugging in x and y where they belong. This is going to be 1 greater than or equal to negative 1 plus 2 is 1. And that's a true statement because we have the equal to part right here, and 1 is equal to 1. Great, let's check the orange one. This time we're plugging in 1 for y and negative 1 for x into the orange equation. This is going to end up being 1 greater than negative 6 minus 8, or 1 greater than negative 14. And is 1 bigger than negative 14? Yes. So since I got a true mathematical statement for all 3 inequalities when I plugged that in, this would be a true in each one. So yes, it is an inequality, or it is a solution to the inequality. Again, if you get a coordinate and you just want to see is it a solution, you have 2 options. If you're given a graph, just see if it's in the shaded region. If you're not given a graph, go ahead and just plug that number in and see and evaluate to see if that is a solution. On the inside of your notes, we're going to be working on actually graphing and writing these systems of linear inequalities. It's very much like graphing lines, so we're going to need slopes and y-intercepts, but remember also we're going to have to decide if the graph is dashed or solid and whether to shade above or below before we determine where the regions are. But that is all about the inequality that you're using. Now, before we begin this first problem, in classic me mode, there is a typo on this problem, so I need you onto the second equation to just mark out the or equal to part of that equation and add in that this is a negative x. Now it actually matches the graph. Again, so sorry, classic me that there's a typo on here. But we want to go ahead and shade the appropriate region. It has been graphed for us, so we already have the slope and the y-intercept and the dashed solid line taken care of. All we care about is the shading. For the first symbol, which is the line that crosses at 2, so this is the solid symbol, we have greater than or equal to. Greater than is shaded above, so I'm going to shade in everything above that graph. Now, because shading can get kind of gross, I recommend that on your notes you just kind of shade by drawing lines perpendicular to the line that you're talking about. Otherwise, your shading is going to get real ugly real fast. For the second equation that we fixed, remember the coordinate or the inequality we're using is still greater than, so I still want to be shading above the dashed line. So I'm looking for the line that crosses at 0, which is again the dashed line, and we're going to go above it, which is all the stuff up here. Now a system of inequalities is going to be solved where they overlap, and they overlap right here, which is the second region that the notes have marked. So we're going to answer that the appropriate region for the shading is region 2. Now that's not quadrant 2, okay, we're just numbering the different areas that are made. We have the blue area, which is 1, the multicolored area, which is our solution set, 2, the red area, 3, and then the blank area, 4, just to designate the different parts created by this system. Again, this is not the quadrants, obviously. In number 6, we have these equations here, and again, it's already graphed for us, so all we need to worry about is shading. So if we look at the first inequality here, it is less than. Both of the less thans shade below, and we're looking for the dashed line that goes through 2. Here's the dashed line that goes through 2, and I'm going to go below that line, and I'm going to start shading it in delicately so that I don't ruin my paper with a bunch of pencil markers. The second inequality here is a solid line, but is also a less than inequality, so I'm also shading below. It doesn't always match like that. That just happens to be like this in the notes. They're both below or both above. So we're going to go to the solid line that crosses the y-axis at 0, and we're going to go below it, which is all the stuff here. So which region on this graph, what number, 1, 2, 3, or 4, are all of the solutions? Region 4 is where all of my solutions would be, because that's where the double shading is, or the overlap in the shading. So that's all fine and dandy that we want to be able to go ahead and identify where solutions are, but sometimes, most times, it's not going to be previously graphed for you. We're going to have to do the graphing ourselves. Now we need to remember a few things. Like we said on the front page, we said that the slope was the rise over the run, and the y-intercept was where it crosses the y-axis. I also want you to remember the difference between Hoy and Vux lines. Hoy lines are horizontal, so they should be flat, like a flat line of 0. And vertical lines go up and down, or have a slope that's undefined. So these first two equations, because they only have one letter in them, are Hoy-Vux equations. The first one, y less than -2, is Hoy. And since it's using this symbol right here, this Hoy line is going to be dashed and shaded below. So I'm going to go ahead and draw a horizontal line that crosses the y-axis at -2, and here's my dashed line. Remember, it's dashed because it does not have the line underneath it. There's my dashed line. We're going to wait to shade to the very end, but we know we're going to shade below that red one. For the second equation, that's a Vux line, so it should be vertical. We again know that it's going to be a dashed line because there's no or equal to underneath that line. But this one says greater than, which means when we come back to shade, we're going to be shading above that line, or where the numbers are bigger. So here's -1 on the x-axis, and here goes my dashed line. All the way across my graph, I have my dashed line that is vertical. Now the third equation is not a Hoy-Vux equation. I'm going to have to remember what the slope, 1/2, and what the y-intercept, -3, do for my graph. That means I'm going to begin graphing at -3, and to create more points, go up 1 over 2. Repeating that across my graph until I have enough coordinate points that I can draw my dashed line. It's dashed because there's no or equal to line underneath that symbol. And since it's greater, it's going to be also shaded above. So I have this nice line across my graph. Make sure it's a nice line. And we're going to shade. We want to shade below the red line. We want to shade above or bigger than the blue line. The right side is where things are bigger, since those are bigger numbers. And we're going to shade above the green line. Do you see why I told you to wait to maybe shade later? Because this kind of gets messy unless you notice the region where all three colors overlap. There is a little triangle right here where all of the shading overlaps. That tiny little triangle right there with 2 dashed lines and 1 solid is my solution set. It's so small. And that occasionally happens. Now, hopefully your graph doesn't look crazy messy and that you realize that there will be an overlapping section for inequalities. Let's do another example. Now, none of these are Hoy-Vux lines, which is great because now I get to practice doing slope and y-intercept. For the first inequality, which has a greater than or equal to sign, the slope is 1 and the y-intercept is -2. Since it's got the or equal to underneath it, I know this is going to be a solid line, and since it's greater, I'm going to end up shading above. I don't think I wrote the negative, but that should be -2. I hope I said that out loud. So here's me starting at -2 and having a slope of 1, which means I go up 1 over 1, all the way across my graph until I feel confident that I can draw a nice solid line all the way across my graph. Oh, phew. There's the first one. We'll come back and shade later so it doesn't get crazy. For the second one, that symbol is less than, and my slope is -1, and my y-intercept is a +2. Since it's less than, it's going to be dashed, and less than is below. Okay, so this one starts me at 2, and it has a slope of down 1 over 1, down 1 over 1, down over, down over, down over, across my whole graph until I feel confident that I can draw a nice dashed line all the way through these points across my whole graph. Make sure it goes to both ends of the graph, and then give me some arrows. We'll come back to shade. The third equation has a slope of 4 and a y-intercept of 4. Now we'll go ahead and write 4 as a fraction just because it's a little bit easier to count my slope that way. 4 is 4 over 1. This is still going to be solid, shaded below. Fabulous. We start at 4, but my slope is going to go up 1, 2, 3, 4 before I go over 1 at all. I'm going to go up 1, 2, 3, 4, and over 1, 1, 2, 3, 4, until I have a really nice line across the whole graph that I can make solid playing connect the dots. Woo-wee! There's a system of equations because I've just drawn lines. Now it's time to shade. Here's where it gets messy, so be careful. For the first equation, the red solid line that goes through -2, we're going to shade in above that. For the blue line, what is dashed and goes through 2, we're going to shade in below that. For the green solid line, we're going to shade in below that, underneath it. Now that looks messy, but do you notice that there is a dashed and solid region right here where all of the colors overlap? That is called the solution to my system of inequalities. That's where all three colors very messily overlap. So let's write a little bit. Explain how we know if an ordered pair is a solution to a system of linear equalities given a graph. So remember, this is the one where we are given some graph and we have two inequalities. I'm just throwing something out here that looks something like this. How do you know if an ordered pair is a solution to this system? Now, hopefully you're thinking something along the line of the shaded region, Miss Quigley. That's fabulous. So let's write that down. We're going to say that solutions are in the region where all the colors or all the shading overlaps. So we're looking in the super shaded region. So the only other thing I can have you do is have you work backwards and write the system of equations represented by the graph. All we need to do is do y, pick some symbol, find the slope, pop an x next to it, and give me the b. So this is going to be one of these symbols, less than or equal to, greater than or equal to. Your slope is going to be your rise over your run, and the y-intercept is just going to be, again, your y-intercept. But remember, there's also a possibility that we have Hoy and Vux lines. So if you have one of those, you just write it with the y or the x only. Let's do, and I'm going to color it or highlight it in red. We're going to do this one first. Where does that graph cross the y-axis? At 0. And how much movement does it take to go from that good point right there to the good point I've highlighted on your screen? Up 1 over 4. So we're going to have y, some symbol, up 1 over, I said 4, but I definitely mean 2. So sorry, 2x plus nothing. We just need to figure out the symbol. Well, that line is dashed, so it's definitely not got the little line underneath the symbol. And since the shading is underneath it, we're going to go with the one that's dashed and below. That's your less than symbol. Double check that it looks like your left hand. Fabulous. Let's do this blue one. Where does this blue line cross the y-axis? -2. And how much movement does it take to get from that y-intercept to the next coordinate point? I had to go down 1 and then jump 2. So my equation would be, or my inequality would be y down 1 over 2x minus 2, or plus -2. Then all I need is the symbol. This line, definitely dashed. The shading, definitely above. The symbol that is dashed and above is greater than, should look like your right hand. All that's left is this vertical line right here, and hopefully you're like, vertical line, that's going to be a Vux line, which only means that there's x and some number. That number is the number where it's crossing the x-axis, 2. Now we need the symbol. Well, this line's very obviously dashed, and since we're shaded on the left side, we're going to use the less than. Left side, less than. So it should look like your left hand for the left side being shaded. Amazing. So again, writing the inequalities is not hard. You just need a slope, which is the rise over the run, and you need a y-intercept, which is where the graph crosses the y-axis. You pick the symbols based on the solid or the dashed lines and where it's shaded.